Hi there, welcome to your lesson on linear functions. Here we have a good example of a linear function. We see something in the real world that is modeled with a line. We'll talk about this example very soon. To begin our conversation about linear functions, we need to differentiate between direct and partial variation. On this graph, we have both direct and partial variation graphed. Can you tell me main difference you see between these two lines that are graphed on here? One is direct, one is partial. What's the main difference you see? I hope you noted that the red line passes through the origin, therefore it has a y-intercept of 0. When the y-intercept is 0, we can actually say there is no y-intercept. I mean, there is, but in the equation, we don't see it because it's 0. So let's take a look at that, because that is the main difference between direct and partial variation. Direct variation looks like this, whereas partial variation looks like this. This one here is more like our traditional equation for a line, mx plus c. This is our y-intercept, this is our slope. Over here, you can see that it's missing the plus c portion, which is the y-intercept. Another way to think of that is if the y-intercept is 0, it would be plus 0, and therefore we don't include it. And that's exactly what's happening on the red line. It has a y-intercept of 0. In other words, we don't need to write it here. So direct variation is that kind of situation. Partial is a more typical linear equation. So let's take a look at what this graph is representing. Here we have time working in hours, and here's earnings. So basically, these are two people perhaps, and how much money they make based on how long they work. Let's take a look at making these equations more detailed then. In this one here, for the direct variation case in red here, I'm going to write it in function notation, E of t. So earnings based on time. So looking at that one, so in function notation, I wrote E of t. That means earnings based on time. So earnings, y-axis, t, x-axis, that's what we have. What is the equation of this one here? Again, we don't have a y-intercept because it's 0. All we need is m, the slope. So what is the slope of this one? How much are we earning per hour? Well, looking closely here, we can see for 1 hour, $3. For next hour, another $3. So our slope is 3 over 1. So the equation must be 3t, using t for time here on the x-axis. Now make an equation for the partial variation situation. So look at the slope, but also look at the y-intercept. In this case, our earnings based on time are 2t plus 4. The plus 4 is our y-intercept. The 2t is our slope, or our rate of earnings. $2 for 1 hour. $2 for 1 hour. Notice that person's making less per hour, but they come in even with 0 hours and make 4 just for arriving on the job. Okay, so that's a discussion of direct versus partial variation. Let's continue looking at direct variation for the next little bit. So a linear model with this equation, y equals mx, relates to variables x and y that are in direct variation. So that's what we're looking at, right? Without the c, with a y-intercept of 0. So the graph has a y-intercept of 0. The gradient is called the constant of proportionality. And the gradient is found how? Well, look at this equation here. And if we rearrange this and solve for m, we could divide by x over here, and we get this. So we can rewrite this equation in this form. And basically that tells us that for any point on the graph, if we divide y by x, we will get our slope for a direct variation situation. So here's an example of that. Here we have a conversion graph for pounds to kilograms. If you have, for example, 5 pounds and you go here, it's about, what was that? About 4 kilograms, or 10 pounds is about 4 and a bit kilograms. Okay, so this is a conversion graph. Now, is it direct variation? Well, how do we know? First thing we look for is that it has a y-intercept of 0. In this case, it does. So this is a direct variation graph. So now we know the equation is going to be like this, and we know the slope is going to be found by doing y over x, because we can move that x over here. So let's find the slope. To find the slope, we take any point on here to do y divided by x. Let's try. Here's a point. That one has a y value of 9, x value of 20, so 9 over 20. Change that to a decimal. That is 0.45. So that means if the slope is 0.45, our direct variation equation for this line here, or this relationship, is 0.45x, mx. No c value again, because it's just 0. Okay, so now that we have that model created for this pounds to kilograms conversion graph, we can use the model to convert. 17 pounds into kilograms. So use this equation. What's 17 pounds turned into kilograms? And then what is 25 kilograms turned into pounds? And now make sure you know which one is y and x. Let's try. First one, 17 pounds. So pounds is your input value, goes in here, multiply by 0.45, and we get 7.65 kilograms. Second one, you are given a kilogram value, so you're given the y value, put y here, and solve for x. 55 is the answer there. All right, you could hear the dog in the background. He says, I canine do math. Okay, let's look at the next problem. So we have some situations here. They're all going to be direct variation, and I want you to create the model for each one. Here's the first one. The weight of a certain type of wood in relation to its volume. So weight based on volume. That means weight is going to go here. Volume is going to go here. Weight based on volume. All right, looking at just the values you're given. If you plotted them, if you had to find the slope, what would it be? And they are direct variations. So remember, to find the slope, you can just do any y value divided by any x value. Okay, I hope you, well, if you plot it, you have that. You connect them, confirm it's direct variation. So take any y value divided by any x value, and you get a slope of 0.9. So our direct variation relationship here is weight based on volume, and it's 0.9 v. That 0.9 again can be done, gotten from dividing 0.9 by 1 or 1.8 by 2 or 2.7 by 3. No matter what pair of points, if you divide them, you will get your m value. Let's try the next one. The number of pounds in weight relating to a weight in kilograms. So again, this is pounds to kilograms, just like we did before. So here's K, kilograms, here's pounds, pounds based on kilograms. And let's see, 2.2 goes in there. What would the next one be? The next one, and then what's your equation? Okay, 1 pound equals 2.2 kilograms, so 2 pounds is 4.4, so 3 pounds is 6.6. Direct variation, if you plot the points, you get a relationship that looks like this, passes through 0. And again, it's kilograms here. Okay, the model here should be weight in kilograms based on weight in pounds is 2.2 times p. Try another one. The circumference of a circle in relation to its radius. So radius are the inputs, circumference is the output. Remember what the formula is for finding circumference? And let's see if you can figure this out. Okay, we know circumference is 2 pi r. So 2 pi times 1 is 2 pi. 2 pi times 2 is 4 pi, and 2 pi times 3 is 6 pi. There's our circumference. If you plotted those, you would get this graph that shows direct variation. And we have circumference based on radius. So again, get the axes right, and that helps you determine the function. So what is it? It is circumference based on radius equals 2 pi r. Situation 4, try this one here. Okay, the price you pay at a shop in terms of the regular price are, if there's a sale, today you pay 15% less. So there's a sale. So the price you pay based on the regular price. How do you figure that out? Here's the regular price, 1, 2, 3, and so on. Here's the price you pay. Well, you pay 15% less. That means you pay 85% of the original. So this would be 0.85. This is full price. This is 1 minus 15%, which is 0.15. And then same thing for 2, 1.7. And for 3, 2.55. Plot those points, you get this direct variation graph. And we have the price you pay based on the original price. So what's our function? Price based on original price is 0.85 R. So 85% of the original price is the price you pay. Great. So going back to this again, just to recap one more time, direct variation looks like this. And the graph will pass through a y-intercept of 0. Therefore, we have just mx, no y-intercept. Partial variation looks like this. So let's shift our focus from direct variation now to partial variation and look at some examples like this. So here's a partial variation example. This is the one from the opening slide. We have the height of a maple tree over time based on age here in years. And you can see it's rising up here. And you can clearly see here that the y-intercept is not 0. So right away, this tells us this is not direct variation. This is partial variation. We need a full y equals mx plus c formula. So can you write it for this one? Okay, I see a y-intercept of about 4. I'm approximating, but I think it's not halfway, so I went with 4 here. Now, what's the slope? Slope might be a little harder to see here. I came up with a slope of 7. I believe I used a point like, well, you can look at this one, for example, or some other points, and I saw a rise of 7 and run of 1. Let's take a look. From here up to here, over to here. So if this was 4, and this point I think about as 11, then it went up 7 to get to here. Okay, maybe you have a slightly different slope. It's a little tough to see on here, but perhaps a different answer could work here also. Now I have this equation. I'm going to rewrite that in terms of function notation for here. Height based on age. So I put height based on age as your input. Great. Now here's our last problem. We're going to look at the same thing, function notation for a partial variation situation. The situation is this. Here we have a pretty famous person. In August of 2018, Ralph Van Hoole, this guy here, he won the 3rd edition of the Sun Trip. It is a solar bike race aimed at promoting renewable energy. So you can see his bike here has these giant solar panels. And he did this giant trip. He completed 12,000 kilometers. That's how long the race is. That's pretty incredible. It took him only 49 days to do that. And the total distance traveled t in relation to days of travel d can be modeled by an equation and a graph. Okay, so we're going to create a model for that in just a second. So first step, assume he maintained a steady pace. Of course, paces change, but if you were to represent his journey with a steady pace, completing the same distance every day, and you were to graph this distance versus time of his journey, would this be direct variation or partial variation? Well, it would be direct because at day 0, he had ridden 0 kilometers, right? He has done nothing when it's 0. So we have that y-intercept of 0. So now find the unit rate. In other words, the slope. What is that slope as a unit rate? And then write the direct variation model. So what is the slope? And then what is the equation? Okay, so the unit rate. How can we find that? Well, simply we can take the full journey, 12,000. We know it is direct variation. It's going to look like this. And we know, again, in direct variation, we can solve for m by doing y over x. So take one point you know, and one point you know is that he finished at 12,000 kilometers in 49 days, right? So x value 49 days, y value 12,000 kilometers. So we divide those two values and we get our slope. And this can be the slope, of course, but when you divide those two values, you get a per day rate, which is your unit rate, 244.9 kilometers per day. So that's a lot of kilometers in each day he went on this bike. Okay, great. Now that we have our slope, we can write the model. So the model is 244.9x. Okay, this is direct variation. Okay, so state the domain and range. We've talked about this during this unit. Domain are the inputs, range are the outputs. So what are the possible inputs here? And remember, in this model, our x, that's our domain, right? Our x values are the days, because it's kilometers per day. So what are the possible inputs for days of this journey? Well, we know the domain has to be from 0 to 49 because he started at 0 days and then he ended at 49th day. So that's our domain, all the possible x values, or d values in this case. Distance. Sorry, I didn't match this up. I should have matched that up. So let me pause it and make that change. Okay, so I added it here. I took my yx model and wrote it more in functional notation based on what it asked for here. Distance traveled based on days of riding. Okay, T of D equals this. And now the domain makes more sense. It says the D values can be between 0 and 49. So 0 to 49 days inclusive. How about the range? What's the possible range? Well, the range we know is the total distance he's traveled, and it can be from 0 to 12,000 because we know that total distance is 12,000 at the end. So the range can be anywhere from 0 to 12,000 kilometers. Okay, great. So here is a graph that shows one of these is his model. So first of all, that's the first question. Which graphed line represents his journey? Because let's say that while he's traveling, other people kind of join him or maybe help to promote the race by joining him a little bit. So which of these, first of all, represents his journey based on our model? Well, we know it's the red one because it is direct variation. It begins at a y-intercept of 0. So there's his model. And you can see from 0, it goes from 0 to 12,000 kilometers. And if you trace this down, that's 49 days. Great, that makes sense for his model. Next question. During his journey, some riders joined Van Hoele for portions of the trip. And first one, describe the journey of the riders shown in blue. So in words, what's going on there? And talk about their speed, talk about where they started, when they joined Van Hoele. Tell us as much as you can. Okay, looking at that one, we can say this rider began about 3,000 kilometers ahead. You can see Van Hoele began at 0, but this person began 3 kilometers ahead of him. All right, he moved at a pace of about 100 kilometers per day, and I determined that just by picking 2 points along here and finding out the slope. So about 100 kilometers a day, which is quite a bit slower than Van Hoele, who's moving at 245 about kilometers per day, right? And you can see there's less slope, so you can see they're moving slower than he is. So they're moving slower, and meaning that Van Hoele caught up within 20 days. So you can see he's catching up, and that 20 days right here, those two lines intersect. So at about 5,000 kilometer mark, Van Hoele caught up to this rider who had started way ahead of him, and then he was ahead of him after that. Okay, next. So describe the journey of the rider shown in green. Give as much detail as you can. Okay, green rider. This rider began at 8,000 kilometers ahead, so you can see they're 8,000 from the starting line. And they rode in the opposite direction. This is important. Their distance from the starting line is decreasing while his is increasing, right? He's moving away from the starting line. They're going towards the starting line. Okay, so if they're going in opposite direction, they also met him at that same day 20. They met there just like that other rider. They all kind of met on day 20 because at that point, this person has gone so far back and Van Hoele is so far from the starting line, they meet. All right, so moving at about 150 kilometers per day. So again, I found the slope of this person's graph. He will meet Van Hoele and the other rider about 20 days into the journey. Okay, great. So you need to be able to decipher graphs like that. And again, we began with Van Hoele's journey, which is direct variation, but the two other riders is not direct variation. So last thing, could you write an equation for both the blue and the green rider? Try that now. Okay, let's check. So blue rider's equation is here. And you can see again, the starting place, y-intercept, and then their speed. And again, his is direct variation. You can see because it has no y-intercept, but here, this one is partial variation. And now the green rider's equation can be like this, starts at 8,000, slope is negative, going down, negative 150. Even though their speed is 150 kilometers per day, it is negative 150 because it's bringing them closer to the starting line. Okay, great job. We will see you soon.